And now for proof of part 4. Okay, we're given this orthogonality. Remember the V means column space. We have the column space of a transpose, which is effectively a row space. But the V symbol was introduced as column space, so we need to put some transposes in there. We get the orthogonality. Then we get that the rank of A is the sum, basically the sum of the rank of the top half plus the sum of the rank of the bottom half. Or the second part, we're looking at left and right halves. And when we've got that orthogonality, then we get the rank of A is the rank of the left part plus the rank of the right part, which isn't surprising. The orthogonality comes with some linear independence. Oops. Okay. So let R be the set of rows of A altogether. Let R1 be the rows in the top half, R2 the rows in the bottom half. When we look at the column space of the top half transposed, this is the row space of the top half. And when we look at the column space of the transpose of the bottom half, this is the row space of the bottom half. Very technically, it's isomorphic to these row spaces because we did ultimately have column spaces, which means all of the row vectors will come out of this little procedure written as column vectors. So give me a little bit of a break on that. I can clean it up by throwing transposition somewhere in here or throwing isomorphic to somewhere in here. It's the dimensions we're interested in, and we're good on that. So the row space of A then would consist of all linear combinations of rows from the first half plus rows from the second half. It's the span of the rows. Since we've got this orthogonality, we were given that orthogonality by hypothesis, then when you take a sum and you've got the orthogonalities, then that's when we got the direct sum behavior. So then we'd have this direct sum type behavior in terms of first vector space plus second vector space. And when we had those types of direct sums, we've said in that exercise, then you can add dimensions so that the dimension of the row space of A is the sum of the dimensions of the row spaces of the other two. Row spaces have come to us as column spaces of transposes. But anyhow, the dimensions add as claimed, and so the ranks add as claims. After all, the ranks are dimensions of row spaces or column spaces. We know those to be equal. Okay, the second part involves a column, so we'll do the same kind of thing. It's actually a little bit easier because I don't need that transpose stuff getting in the way here. Let C be the columns of A, C sub 1, the columns in the first, the left-hand side half, C sub 2, the columns in the right-hand half. Then, when we take the column space of this partition matrix, and it's just straight up the column space, similarly for the right-hand part. So, columns of A, column space of A is the sum of these two. It's this all linear combinations of columns of matrix A. This includes some of them, and this includes the rest. So that is the column space. Since we've got, by hypothesis, orthogonality of these two spaces, then we can write the column spaces as direct sum, and we can add dimensions again, or we can add ranks again as claimed. So there's a lot of mileage we're getting out of that earlier stuff. That exercise from chapter 2, the stuff about adding dimensions and this equality when we had the orthogonality stuff. Okay, one of the exercises, it lets you deal with a block diagonal matrix we mentioned in passing. That's where we have a matrix A, and it's partitioned, but we have these square matrices. We have these matrices along the diagonals. And then the claim is the rank of A is the sum of the ranks of those matrices along the diagonals. So somewhat related to what we have here, maybe generalization of what we have here. A couple more results. Theorem 3 .3.5 says, let A be an n by k matrix and be a k by m matrix. Notice the dimensions. I bet we're going to multiply them together. Claim is the rank of the product is less than or equal to the minimum of the rank of A and the rank of B. Let's look at that result. So that might, on the surface of it, sound a little weird, that we're getting this minimum thing when multiplying. All right. Well, let's do our usual deal. We'll let the columns of A be these subscripted lowercase a's, the columns of B, lowercase subscripted b's. For the product, because we are dealing with three matrices, let's let the columns of the matrix AB be C sub 1 through C sub n. So each of these subscripted lowercase letters are in fact vectors. All right. If we take, I mentioned this earlier, matrix A times vector X, through the computation by our definition of matrix multiplication, this gives a linear combination of the columns of A, and by the way, the coefficients are the components of vector X, an essential property of matrix multiplication. We remarked earlier, solving AX equals B systems of equations is looking for vectors in the column space of A. Yeah, that's because when you multiply A times vector X, you get a linear combination of the columns of matrix A. So in other words, for any X, a vector of appropriate dimensions, AX is an element of the column space of A. Okay. We know that if we take A times B sub I, we're getting out, and that produces column vectors as well. We set this up where when we multiply matrix A times matrix B, we get the resulting columns. So matrix A times B sub 1, that'd be the first column of the product AB. So that would be what we've denoted C sub 1 and so forth for the other columns. So we have C sub I equals A times B sub I as I ranges from 1 to m. The columns of that matrix product are produced as given. So we're getting these C sub i's being A times B sub i's in this observation here, being vectors in the column space of matrix A as well. All right, so what we just accomplished was we showed that any column of the product AB is in the column space of matrix A. So every vector in the column space of the product is a vector in the column space of matrix A is what we've shown. So there comes a minimum, there comes an inequality right there in terms of that set inclusion really. So every linear combination of the columns of AB is also a linear combination of the columns of A. In other words, the column space of AB is a subspace, subvector space of the column space of matrix A. So the dimension of the subspace is less than or equal to the dimension of the big space, or since these are column spaces, the rank of AB is less than or equal to the rank of A. All right, nothing special about A. I guess it was on the left. In the product, so I need to be a wee bit hesitant there, but we're going to borrow that result to introduce matrix B now. All right, the rank of A equals the rank of A transpose, we said, 3.3.2. Rank of B equals the rank of B transpose, so the rank of AB equals the rank of AB transpose. Just interchange the rows and columns. Of course, we know the dimension of the row space equals the dimension of the column space. So that's how we can draw these conclusions. We actually stated it, I think, as a note. So since we know the rank of a product behaves in a certain way, if we take the rank of AB, we can write that as the rank of AB transpose. You know how transposes interact with matrix products. That gives us a rank of B transpose times A transpose. All right, so here's a product. I want to use what we already have, which is when I take a rank of a product, we get something less than or equal to the rank of the matrix on the left in that product. Okay, we got a product here, and regardless of whether it's A or B or A transpose or B to whatever. We got a product of two matrices. Whenever we have that, we should get that the rank of that product is less than or equal to the rank of the first of those in that product. So using this, technically we're replacing A with B transpose and replacing B with A transpose. But we get from that the inequality is used here to get rank of B transpose. Hey, rank of B transpose is the same as the rank of B, and there's how we get the other part. So we get the rank of AB is less than or equal to the rank of B. Rank of AB is less than or equal to the rank of A from above. So the rank of AB is less than or equal to the smaller of the two, because it's less than or equal to both of them. Another result concerning this time some addition of matrices. We take two matrices, A and B, same dimensions. Then claim is the absolute value of the rank of A minus the rank of B is less than or equal to the rank of the matrix sum. There's the matrix stuff right there with the addition. Is less than or equal to the rank of A plus the rank of B. Okay. I got no real intuition on this one. I need to be thinking in terms of column spaces. I mean, it looks plausible just with the symbols. But remember, when you say rank, you're talking about dimensions of row spaces and column spaces. I don't see how, intuitively, I don't have a hold on why adding the matrices together would produce this kind of thing. Maybe you lose some linear independence, probably something to that effect. All right, well, showing this is actually not very hard because we got a fair amount of equipment behind us at this stage. Consider the following. Let's take the partition matrix, A, B, 0, 0, multiply it by the partition matrix, M by M identity, 0, M by M identity, 0. Theorem 3.2.2 tells you how to multiply these. Basic row times column stuff. So if you multiply these two partition matrices together, we'll get A plus B, 0, 0, 0. Of course, the zeros represent matrices of appropriate dimensions. Okay, Gentle approaches this in a slightly different way, but I want to look at it in terms of a product of partitioned matrices, and this gives us an A plus B over here. Inspiration, I want to compare ranks of A plus B to ranks of A and B. A and B and A plus B. And we got a product there. All right. Let's see, we just saw that when we have a rank of a product of matrices, we get less than or equal to the minimum of the rank of the constituents. So if we take the rank of A plus B with the zeros on there, this matrix here, the rank of that, it's the rank of the product of these two. Well, the rank of the product of these two is less than or equal to the minimum of the rank of the first one times the rank of the second one. Okay. Rank of the first one, rank of the second one. That's less than or equal to, well, now that we're choosing the smaller of the two. So whatever we get up here, well, that's less than or equal to the rank of the first one. Okay, it's also less than or equal to the rank of the second one, but it's the first one I'm interested in. So because we're choosing the smaller of two, whatever I put down here is something that's greater than or equal to. In one case, it's greater than, in the other case, it's equal to, depending on which I choose if they're different in size. But anyhow, that's fairly easy reason that holds. So let's see, we've got the rank of this matrix is less than or equal to the rank of this matrix. Looking good. This matrix we'll use to find the rank of A plus B. Here, presumably, we'll end up with the rank of A plus a rank of B from this part. All right, so let's see. Let's take what we had on the left-hand side, going back briefly. Here we're taking a rank of a partitioned matrix. We previously said that'll give us the rank of the first part, rank of the second part. We picked up an additional inequality in that, if memory serves. So we've got the rank of this partition matrix. Oh no, we're doing it one piece at a time. Now 3.3.4 tells us we do when we got this type of partitioning, we get less than or equal to, this less than or equal to is coming from the theorem, the rank of the left side plus the rank of the right side. All right, we had at the previous slide that the rank of this matrix was less than or equal to the rank of this matrix. Combine that with this inequality to produce the rank of this matrix is less than or equal to this sum on the right-hand side. Excellent. Now think what's going to happen next. You've got a bunch of columns of A, and then you pasted zeros underneath them. We could erase some zeros and you'd get the same dimension space, I suspect. Same thing here, same thing here. A little more involved here because we've got zeros below and to the right. All right, so it's a matter of getting rid of the zeros at this stage. All right, zero matrices in the second rows of these matrices don't affect the rank. So you can drop the bottom zeros. Why is that? Think in terms of row spaces. The rank is a dimension of the row space. I know it's also the dimension of the column space, but I want to look at rows this time. All you've done is add a bunch of zero row vectors underneath in all three of these cases. So we can drop the zeros underneath and get the rank of this partition matrix equals the rank of this partition matrix. I'm still stuck with some zeros in that one. Drop the zeros below here and here, and I can get to the rank of A and the rank of B. Similarly, the rank of A plus B partition with this zero vector of whatever dimensions is the same as the rank of A plus B. Why is that? Well, now I want to talk about column spaces. The columns of A plus B have augmented, or this partition introduces a bunch of columns of zero. So they don't contribute anything in terms of dimensions or linear combinations or anything. So the dimension of the span of A plus B with all these zero vectors is the same as the dimension of the span of A plus B, the columns of. So we can drop the zeros in either case, leaving us with the rank of A plus B is less than or equal to the rank of A plus the rank of B. That's going back up here. So we're taking this, we drop the zeros to draw this conclusion. Dropping of the zeros is justified in between. Asterisk, let's rewrite that. Yeah, let's rewrite that. Okay, so we were trying to show rank of A plus B is less than or equal to the rank of A plus the rank of B. We got that part. And then this other part, well, that's easily established from this. That easily notice that A equals A plus B minus B. So let's take the rank of A, rewrite A as A plus B minus B. Okay, I've got two matrices added together. That's less than or equal to the rank of the first plus the rank of the second. That's what the asterisk equation tells us. That's what the first part we established tells us. So this is less than or equal to rank of the first, A plus B, plus rank of the second, negative B, negative B. We're trying to establish we're trying to compare these to the rank of A plus B. So let's see. Here's a rank of A plus B. It's greater than or equal to, got rank of A on the other side. And let's take this rank of B and move it to the other side, rank of negative B. So we get the rank of A plus B is greater than or equal to the rank of A minus the rank of negative B. Hey, whoops. If I multiply matrix through by -1, that doesn't change anything in terms of rank, right? It replaces all the, I don't know, all the rows with their negatives. All right, well, that doesn't change any linear independence. That doesn't change anything in terms of rank. I could explain it in terms of elementary matrices and quote a theorem if you like, but let's be reasonable. So the rank of negative B and the rank of B are exactly the same. And then we've established rank of A plus B is greater than or equal to rank of A minus rank of B. Okay, that's half of it. All we got to do is, interchange the roles of A and B up here and recycle this argument, and then we'll get the rank of B plus A is greater than or equal to the rank of B minus the rank of A, establishing the inequality as a lower bound as needed. All right, so back to the notes. There's some behaviors on ranks. Okay, let's do a little bit more of this. Up to systems of equations. Yeah, so let's do about one more slide worth of material. All right, if n by m matrix A is of rank R, it's got R linearly independent rows. There's a permutation, e sub pi 1, such that e sub pi 1 times A, permutation matrix, e sub pi 1 times A is a matrix whose first R rows are linearly independent. Yeah, we did that in one of the proofs. So you know there's a permutation matrix that lets you pull the linearly independent matrices up to the top. We did that with, I think it's when we showed row rank equals column rank. We did some of that. Since e sub pi 1a is also rank R, we've multiplied by really a product of elementary matrices. Theorem 3.3.3 allows us to justify that. You know, it's got R linearly independent columns. Row rank equals column rank. Linearly independent is the basis for the column space. So there's a permutation. This should read e sub pi 2. Excuse me, I've updated this. Let me refresh and go to page 4 again. Sorry, kids. Permutation, a second permutation, let's call it e sub pi sub 2, that allows us to permute around the columns. Do that by multiplying on the right. Not an elementary matrix, but a product of elementary matrices of a particular kind. In fact, both of those are permutation matrices. You just swap rows or swap the columns. Left or the right is appropriate. On the left, you swap rows. On the right, you swap columns. So we can take this matrix A and kind of isolate the linear independent part. We can take matrix A and with these permutations, produce a matrix, call it B, that can be partitioned in a way that isolates the linear independent sub-rows and sub-columns. That's mentioned, and we've used it, so we can define the following. All right, let B be an n by m matrix of rank R whose first R rows are linearly independent and whose first R columns are linearly independent. Then the partitioning up of B as given here, where W is R by R. So I've used the rank, really, of matrix B to do this moving around. And the remaining pieces are of the appropriate size. This is called a full rank partitioning of B. So, you know, the first R columns of B are linearly independent. You know, the first R rows of B are linearly independent. If you'll chop off everything except for the little W matrix, that's an R by R matrix, hey, it's got linearly independent rows and columns. It's a full rank submatrix of matrix B. Yeah, it's R by R, where R is the rank of B, which wasn't explicitly said here, but it's implied. If n by m matrix A is of rank R, for any Q less than or equal to the rank, we can use these permutation matrices as described above to produce out of matrix A matrix which can be partitioned, where S is a Q by Q full rank matrix. All right, so what we did is we pulled Q of the linearly independent rows up to the top and Q of the linearly independent columns over to the left. Maybe not all of them that were available, but only Q of them. And we've created this kind of partition. So this is just a lame version of what we had upstairs. If we take, I mean, it's more general observation. If we took Q equal to R, then we'd have that full rank partitioning that we had upstairs. But we could create these little submatrices. Well, a little submatrix is also, it's a full rank because we built it that way. It could be bigger and still be full rank if Q is strictly less than R. All right, so that's enough of that. We'll stop here and come back and do linear equations. We've only made it through about 4 pages of the notes, so we got a ways to go on this material. So I'll get to working on systems of equations, and we'll do that next.